All right, so it's been a little while since I worked this exam, since this is now it's basically summer of 2021. But I'm working this older one, hopefully to help you guys out. This is the final from fall or spring or something. Let's see. When is this? Spring 2021. Anyway, was when we took this. Although I think down here it says fall 2020. It looks like I goofed and forgot to write that on there. Okay, and this first page you can basically ignore. This was just so that everybody could write in their student number right here, and they would get different numbers for each of these questions. It was to prevent cheating. So what I've done here is I've just entered in the student ID number 1, 2, 3, 4, 5, 6, 7, and I'm just going to enter all these numbers in the blanks in each problem. This didn't really stop cheating, but hopefully it made it a little more difficult. So anyway, so I've already taken all these numbers and written them on the problems, and so when we get there, we will have numbers. All right, so let's go down here. Here's the first page. Indicate whether the following statements are best described as true or false. Okay, number 1, turbulent flow is more chaotic than laminar flow. That's true. That's almost like the definition of turbulent flow. Number 2, or B or whatever, EGL never decreases in the direction of the fluid flow. This is very false. It's pretty much always decreasing in the direction of the fluid flow. The only time it would increase is if there's a pump. Okay. Fluiding exiting the system into the atmosphere experiences zero gauge pressure at that point. That is true because zero gauge pressure is atmospheric pressure. So that's a good one. Okay. In the English system of units, power is measured in foot-pounds. Okay, that's actually work. But the way you can do this if you forgot is you can look at your sheet where they've got an equation for power, and it's gamma HP or HT, depends on if it's a pump or a turbine, times Q. And you can say, well, what is gamma? Well, gamma is pounds per foot cubed. Okay, the HP, the head from the pump, well, that's just feet. And then Q is cubic feet per second, right? So then you can say, oh, well, these cubic feet cancel with those cubic feet, and I'm left with foot-pounds per second. So this would be true if that was foot-pounds per second, but it doesn't have that, so it's false. Okay, a pump removes head from a flow. Well, that's exactly the opposite of what it does. The friction factor F is not a function of Reynolds number for laminar flows. Remember a laminar flow, there's an equation, F for laminar flows, that's 64 over RE. That's for laminar flows. So that very specifically says that friction factor for laminar flows is a function of the Reynolds number. So this is the definite false. Okay, if the HGL is below the fluid, then the pressure is negative. Now this is a little bit complicated, but it is true. And usually, if I was over here and let's say I had a pipe, and so, and I've got an HGL and it's dropping and it drops below the fluid itself. Okay, so this is the HGL. Okay, remember we would define, usually you would say, okay, well, here's some datum. And then from here to the fluid itself, that's Z, and then from there up to there, well, that's P on gamma. And so Z, P on gamma, and then all of a sudden here, Z, and then P on gamma comes back down. Okay, so that is the equivalent of a negative P on gamma, which means we have a negative pressure. Okay, so in terms of gauge anyway. So if the HGL is below the fluid, then the pressure is negative. This is true. This is in terms of gauge. So that's definite. That's a true. This probably could have been a little clearer, I guess. The Bernoulli equation is useful for unsteady flows. This is false. It's one of the assumptions of the Bernoulli equation is that it is steady. So that's just something you just have to know. The buoyant force is the difference between the pressure on the top and bottom of an object in a fluid. That is true. That is really the definition of the buoyant force. And the last one, it is possible for a turbine to remove more power from the fluid than I recover from the turbine. Okay, so let's imagine what this is. So I've got a fluid, it's cruising along, I put in a turbine. Right, so if I remove, say, 1,000 kilowatts from the fluid, or excuse me, 100 kilowatts from the fluid. So the fluid here has, 1,000 kilowatts, and then, kilowatts, and then right here it's got 900 kilowatts because the turbine removed 100. Well, how many of those do I actually get? Well, I'm going to lose some because of just efficiency, right? The turbine's not 100% efficient, so I maybe only get 90 kilowatts. Okay, so let's see here. It is possible the turbine to remove more power from the fluid than I remove from the turbine. Okay, so that is definitely true. That is the way the world works. Okay, laws of thermodynamics. Okay. Anyway, so that problem's worth 10. Obviously, that math there is easy. This one's, well, almost all of them are worth 10 points. I like easy math. Okay, water through the okay, let's see. So number 2, we have one of these. These are one of my, you guys know me. You know that this is my favorite type because it basically brings in everything. Okay, water flows through the contraction shown at Q of this number. If D1 is 4 and D2 is 1, and the manometer fluid has a specific gravity of 0.41. Okay, so that depended on, the student's, what do you call it? Student's student number. So everybody would have had a different number right there. So we'll go with 0.41. What is the deflection of the manometer? H. Okay, so that's this right here is what we're looking for. Okay, you may assume there's no head losses. So when we assume there's no head losses and there's no pumps or turbines, basically they're saying you can use Bernoulli. The only problem with that, I guess, is that you might be concerned about not having that alpha, which could come into play. But I guess not really, because we're on a streamline. It is steady, so it meets all the criteria of Bernoulli. So we're just going to go from here to there, from 1 to 2 on Bernoulli. Okay, so here's Bernoulli. And Bernoulli, usually in these problems, is the master equation. Okay, so I'm going to put it up here as the master. Okay, fully aware that, we're usually going to do the same things over and over and again for these. So, we've got a manometer. Oh, so here's point 1, and here's point 2. And we've got a manometer, and so we're gonna walk from point 1 to point 2. Okay, so I'll start at pressure at 1. So this is the manometer. Okay, and why am I doing that? Because I got to get at these pressures, right? So that's the first step. Let's get at these pressures. Okay, so P1. Okay, I'm gonna go up. So go minus gamma of whatever this thing is that's flowing through here. What is it? What is flowing through here? Water. Okay. Gamma water times capital H. Okay, and then I'm going to keep going up. Plus L. And then I'm going to keep going up plus lowercase h. Right? And then from here I'm going to move laterally in that fluid, so I'm not going to worry about that. And then I'm going to move down in whatever this is. So I'm going to go plus gamma of the manometer fluid. I don't know what we want to call that, gamma fluid, times that distance, which is lowercase h. And then I'm going to go down in water, that L, minus gamma water times this L. And that's going to get me over to this point right here, too, equals P2. Okay, so once we've done that, so the manometer equation, we're going to have to rearrange this, right? And in this equation, we always want to be careful and remember that this is gamma water, and that's gamma water, because water is the fluid that is flowing from 1 to 2 in the Bernoulli equation. So over here, we need to remember that when I rearrange this by subtracting P1 from both sides, that I want to then divide it by the gamma of water and not by the gamma of whatever this, this other fluid is. So let's see here. All right, so we're going to divide by the gamma of water. Gamma water, gamma water, gamma water, gamma water. All right, so before I do all that, I guess as I do that division, so these two gamma waters are going to cancel. These two gamma waters are going to cancel. I've got a minus L right here, okay, because remember that it's going to have that negative sign on it. Wait a second. Oh, there's an error here, isn't there? This last bit should have been a plus gamma, shouldn't it? So that should be a plus sign. Okay, but anyway, so I've got a minus L right here. and I've got a plus L right here. So those two are going to cancel. Okay, so what I'm left with here is, if you do all the algebra here, negative h minus h plus gamma fh over gamma water. And in place of that gamma f, I'm going to put SF gamma water, right? Because gamma f equals SF gamma water from the definition of the specific gravity. And then we're going to do a, right, this L went away with that L, so these two L's cancel. Equals P2 minus P1 over gamma water. Okay, and then these two are going to cancel out. Okay, and I'm left with something really weird, I guess, or whatever. So P2 minus P1 over gamma water. I'm flipping sides here because it just kind of seems cleaner to me. Equals negative h minus h plus SFH. Lowercase h, excuse me. SF lowercase h. SF times lowercase h. Okay, and a lot of times, you know, and it doesn't have to be this way, but a lot of times what you'll see here is that this will be kind of getting written like this. Is that these two will kind of be combined, and you'll be left with negative h. Let's see, that's a 1. Pull out an h. I guess it depends on what you want to be positive and what you want to be negative or whatever. But a lot of times you'll see something like this, SF minus 1 times h. It's not really important that you write it that way, but you could, okay? It looks like in my key that this is the way that I did it. The last thing we would do is this specific weight is 0.41, so we would plug that in, just because it makes it easier. You don't have to do it at this point. Negative h plus, so 0.41 minus 1 is going to be minus 0.59 lowercase h. Okay, so that's what we're going to plug in, right? Okay, so once we have that, let's see. So cool. So now I know P2 and P1, or at least I know how they compare to each other. Of course, it introduces two unknowns, this capital H and this lowercase h. So we'll have to deal with that shortly. Okay, so now let's go on to the z's. We've got these two right here. And we're going to look at our diagram, and we're going to note that Z1 is right here, and Z2 is right here. So the difference between them is h. So if I make this the datum, then Z2 is at a height of z equals h. Okay, so Z2 becomes capital H, and Z1 becomes the datum, or is the datum. Okay. Then the last bit, we've got to get at V1 and V2. And usually the way we get at those, and this isn't going to be any different, is we're going to use continuity for these two. Okay, so maybe I'm going to do that over here, because we've got this going on right here. D1 and D2, right? So from continuity, okay, right. Then what I'll do is I'll say, okay, well, Q at 1 equals Q at 2. So V1A1 equals V2A2. And you guys should already know that, V2 is going to be 16 times V1, but we'll go ahead and work that out. So V1 times pi times D1 squared on 4 equals V2 times pi D2 squared on 4. Okay, and these pi's and 4's are going to go away. And I'm going to say that V2 equals, D1 squared over D2 squared. D1 squared over D2 squared times V1, right? So that's just some algebraic manipulation. And if you plug in 4 and you square it, and you plug in 1 and you square it, you're going to get a ratio of 16. So V2 equals 16 V1. Okay, which really means for the Bernoulli or energy equation, whichever one you choose to use, is that V1 doesn't really matter. Okay, that's just the way it is. Okay, but we're going to go over here and we'll go ahead and we'll make use of that knowledge in this equation. okay, over here. Okay, so let's go ahead and plug all of this in, and let's just see what happens. Okay, wait, actually see, I really screwed that up, didn't I? We've got a flow rate, we've got Q. Okay, so that's messed up. So let's go ahead and do this one more time. Since I know Q is 0.00101 cubic meters per second, so I could say, okay, well, Q equals V1A1. So 0.01 meters cubed per second equals V1 times pi times, what was D1? D1 was 1 centimeter, 0.01 meters squared, divided by 4, right? So V1 is pretty high, really. 7.9577 meters per second, awfully high, right? And if we multiply that by 16 using this relationship right here, we'll say that V2 is 127.32 meters per second. Okay, so that's, you can see that as we plug these, so this one's 16 times as big. When we square these, because they plug into the Bernoulli equation, this one's going to be 16 squared times as big. I think it was 16 squared 256. I think that's right. So you can see that this one is basically, it just doesn't matter, right? We could ignore it in the whole equation and it would make no difference. But whatever. Okay, so we're going to go back over here, and now we have everything we need to plug into this equation. So the first thing I want to do, I'm going to rearrange it a little bit. So P2 minus P1 over gamma water. That's these two right here. Z1 is a datum, so we're going to ignore that. And we're going to have V1 squared on 2G plus this one's H. And this is V2 squared on 2G. Okay, from that, I think we are like 100% ready to plug in. So, so let's do, let's see, V1 was this number, 7.9577. 7.9577 meters per second squared divided by 2 times 9.81 meters per second squared equals P2 minus P1 is this number right here. Ignore this. That's the number of points on this question. Negative H minus 0.59H. So negative H minus 0.59 lowercase h. Okay, H is just a capital H. Notice these two cancel. That always happens. It's a really nice feature of these things. And then we'll go plus, and we've got V2, and V2 is some big number, 127.32. 127.32 meters per second squared over 2 times 32.2 feet. No, 9.81, excuse me. I wish I could say I did that on purpose to show you that everybody makes those mistakes, but I didn't. All right, so then we just have to solve this for H, right? I'm going to go ahead and put in the intermediate steps here. So these H's are going to cancel just because it's going to help me make sure I don't make an error. So negative 0.59 H plus, and I've got a number on each side of this thing. And here you can see kind of what I was driving at a second ago is that, this velocity head is 256 times as big as this velocity head. So, when you start squaring things, it starts to really, it's nonlinear, right? So a lot of times this is what happens. So, so now we'll bring this over to the other side, and then we'll divide by a negative 0.59, and we'll get some number. That will be our answer. Okay, so I'm getting 1,394.9 meters, or H equals 1.39 kilometers. Okay, now you may be saying to yourself, wait a second, that's totally unreasonable, therefore I should throw this problem away, blah, blah, blah. This is one of the problems of this, this exam, is that by giving everybody a different specific gravity here, it creates huge problems, or by giving them their own numbers. And so for a lot of this test, the answers just aren't going to make any reasonable sense. This is, in fact, the correct answer. Clearly, in this case, you would not be able to do this. You would need a different fluid, a different sort of something. I don't know. But I mean, it should have been a sign there was a problem when we started having, fluid moving through at 127 meters per second. So basically on this exam, I didn't worry about realism. And of course, when I gave it to them, I said, don't worry about the realism of your answers. Like, there's just nothing we can really do about that. Okay, so hopefully that's okay with you guys, but that's how we would work this problem. Okay, so let's go down here. Draw the, one last thing to note. This 14 degrees right here, this is a red herring. It was not necessary to know that. Okay, it's not important. The fluid doesn't care about the angle. Okay, draw the EGL and HGL for the system below. Use a solid line for the EGL and a dashed line for the HGL. Okay, so let's see, solid line. Maybe we'll go red for energy. So this will be EGL. Okay, so remember, I like to think about the energy EGL first. 100%, let's think about the EGL, and let's only think about the EGL. Okay, right along here, right, we have an elevation, which is coming from some datum, Z. My pressure head is 0, my velocity head is 0, right? I get to this point, and here's where I'm going to lose energy. I'm going to lose energy here, I'm going to lose energy here, I'm going to lose energy here, I'm going to lose energy with the turbine. And then, I wouldn't worry so much about the nozzle so much. I mean, technically you will lose energy in the nozzle. So, yeah, well, let's just say, okay, you're going to lose energy in the nozzle. Okay, you will gain energy in the pump, right? So this is a plus. All those other ones are minuses, right? And everywhere else we're going to lose energy, and we're going to lose energy at varying rates, right? And really, we've got two widths of pipes. So we've got a width of pipe. This is width 1, this is width 1, this is width 2, or diameter 2, and this is diameter 1 and diameter 1. So everywhere we've got a 1, right? What do we have? Well, we're going to have, we're going to lose energy slowly, right? So shallow slope, right? And everywhere we've got a 2, we're going to have a steeper slope. Okay, so that's something we need to think about when we're drawing this. So every time we hit one of these little circles right here, we're going to lose energy, right? And different people will have drawn this different ways. It's just going to kind of depend on what you feel like, but it's going to be something like that. Some people will draw it straight down like this, which is fine too. It's not critical to me that you get those details exactly correct. Okay, and then we're going to lose energy, but we're going to lose it slowly. So I'm going to draw kind of a shallow sloping line. So it should be clear that it's going downwards, but it shouldn't be going down so slowly as to make the drawing difficult. Now we're going to have a pump right here. And so the pump is going to cause this energy to increase rapidly. I don't really know how high to draw that line. So a lot of times when I hit a pump, I start working back from the other end just so I know how high to draw that line. And so what I'm going to do is I'm going to note that at this far end right here, when I exit, I should have Z. Well, let's go right to the exit here. I should have a Z, right? Because obviously it has some elevation above that datum. But I also am going to have a V squared on 2G, right? V squared on 2G. And that V squared on 2G is going to be fairly big because look how small that opening is, right? So I don't want to discount how big that V squared on 2G is. It exists, it's real, and it's a pretty sizable value right there. Okay, so that's something to remember. Like that's kind of where I'm going to end up. Okay, now I also want to note that so now I'm going to start working backwards here, to figure out how high I want to go there, right? And so I'm going to erase that line that I just did because obviously that's not the correct line. But I want to note that, okay, so I've got kind of notes here going on about the slopes, right? So where it's, wherever it has a diameter of 1, I've got a shallow slope, and wherever I've got a diameter of 2, I've got a steeper slope. So like right here at this exit, I'm going to go ahead and say that that's the steeper slope. Now, I don't know how steep that slope is, but let's make it sizable, right? Now what's going to happen, of course, is that, right in, once it gets back to about there, I'm going to be back on that shallower slope. So we're going to kind of curve that line like that, right back into that shallower slope. Then we're back in that shallower slope all the way back to that turbine, right? Because it's all along that pipe. Okay, remember I hit the turbine, I'm going to lose some energy, something significant. Okay, I don't know how much. I mean, obviously, this is totally qualitative, so that it could be a little tiny drop. I just need to see that that there's a drop. And then we're coming out the other side. We're still in a kind of a D1 pipe, a diameter of 1. So we're going to come back. We're going to hit this little knob or whatever here. I guess I should somehow demonstrate that I'm at these locations. So it never hurts, stuff like that. Okay, now in here, it's, that narrow pipe. So we're going to lose energy. Oh, okay, sorry. First, I need a little head loss right there. So I want to kind of get the steepness here, right, And so we're going to go fairly steep in here. And it looks like I'm going to end up working well into the space for the other problem. I apologize for that. This is, of course, why we drew it. So there's a little head loss right here, right, associated with this transition. And then we're going to have kind of like a, little shallow, we're back in a 1 pipe, right, and a diameter of 1 pipe, right? So there you go. There's our HGL, or our EGL, right? And I'm going to kind of make these dotted so that they're clear that that's not the same line, right? Okay, so that's our energy grade line. And so, if we wanted to kind of talk through it, well, we would be cruising along, then we lose energy here because of the entrance. Then we lose energy slowly along a diameter 1 pipe. We gain energy due to the pump. Then we continue to lose energy slowly because it's a diameter 1 pipe. We lose energy because of this transition right here. Then we lose energy quickly because it's a narrow pipe, a diameter 2 pipe. Then we lose energy due to this transition. Then we lose energy slowly because we're in a diameter 1 pipe. Then we lose energy quickly because the turbine. And then we lose energy slowly because we're in a diameter 1 pipe. And then as the fluid accelerates, we start to lose energy quicker and quicker as we exit. Okay, and we finish some distance v squared over 2g above that nozzle because we have velocity right there. Okay, I could label these and I could say, well, this is HP. This little guy right here, this is a little minor loss. This one's a minor loss. This is H sub T, and that's it. I mean, I'm not going to, sorry, there's also a head loss right here. I don't normally ask you to draw all that, but, it's there if you wanted to do it. Okay, so that's the EGL. The HGL, okay, which I'll draw like as a dotted line. The only thing we got to remember with that is, and it's kind of similar to this, 1 and 2, is we've got v squared on 2g, right? V squared on 2g, v squared on 2g. Okay, so if I'm in a diameter 1 pipe, that's the larger of the pipe, v squared on 2g is going to be small because it's not moving as fast as through the narrower pipe, where v squared on 2g is large by comparison, right? So if I'm assuming that right here, has v squared on 2g, that means v squared, so this large is equal to that right there, okay? The small is whatever the small is, but it's got to be smaller than that, okay? So that means the distance between these two lines, okay? So right in here, there's no movement, so, it's right on top of the other line. And now we're going to go down, and we're just going to kind of follow this thing along, and this will be my small v squared on 2g. This is this distance right here, v squared on 2g. Okay, and everywhere within a pipe 1, in a pipe with a diameter of 1, that's the v squared on 2g we're going to use, okay, more or less. Now, obviously, none of us are perfect, so we're going to do the best we can. Okay, and so that's the EGL right there. And that one's hard to see because it's right in the middle of those words. okay? And then, so, we start going down steeper, and we go down steeper, okay, we're in this narrower pipe. So I need a V squared on 2G that's about this big. Okay, so, again, I'm going to do the best that I can. So something like that. Okay, so I'm going to go ahead and, connect those dots. Okay. Now I'm in the narrower pipe again. So I'm going to do like, I don't know what that distance is, something like this. Like that. Okay. And I remain in the narrower pipe. Okay, and then in this last little bit, cruising along, and then it's going to basically transition from one V squared on 2G to the other because the pipe narrows. So it's going to kind of do like, whoops, all the way down to that exit. Okay, so you'll notice the V squared on 2G is enlarging as it hits the nozzle. So I guess that transition shouldn't have happened until right about there. So maybe we should clean that up a little bit. So this should be straight until about right there, and then it kind of goes in. Okay? So there you go. Okay? So this distance is V squared on 2G. V squared on 2G. This is V squared on 2G. And the only thing we need to really remember for that is, what kind of pipe are we in here? Okay? Yeah, that's it. It didn't ask for anything about, where might it cavitate or something like that. I think it would be pretty difficult to find a cavitation spot on this one. As far as I have it drawn, this is the pressure is between the Z and the HGL. So this is P on gamma. This is P on gamma. All right, P on gamma is between the Z and the HGL. So we could draw, this. And if you wanted to know, where is it going to cavitate? This is the most likely spot right here as drawn. That's where the pressure is the lowest. I guess you could make an argument that the pressure is lower right here, but it's going to be impossible for this to go negative. And the reason for that is because it's basically locked to zero by the exit, right? And in order for the flow to continue forward, the pressure has to be positive. So, you can't get a negative pressure right before a nozzle. I'm saying that. I'm trying to think of a situation where maybe you could, but I can't think of a situation where you could. So I would accept that. I would expect that. I guess if you guys put that it was right here, I guess that's possible. But this is really the only spot in the system where you could expect a negative pressure might happen. And you might draw it that way, right? You might draw a steeper, energy loss than I do, right? This is all qualitative, so who knows what would happen, right? So anyway, so we're going to on to the next one. That one worth 10 points. By the way that I grade these is I'm looking for, did you include all these little things like this and this? Not necessarily that you labeled them, but that the pipe went up and down in the places it's supposed to go. Up and down, and then the slopes of these lines, and then this V squared on 2G. I want you to kind of get those sizes approximately correct. Okay, so that's really the way I grade it. If the only thing that's what I call a major error is if you have the EGL go up when there's not a pump, that is what I call a major error. And I'll take off 4 out of the 10 for something like that. Usually if somebody does that, there's going to be a lot more problems than just that. But just it kind of means you don't really understand what you're doing with this particular problem. So just be very aware of that. Okay, so a cylindrical object with a mass of m. So this mass right here is 57 megagrams. Okay, that's a really annoying unit. And I think I got a lot of, so this, that's just coming from somebody's student ID number. And so remember, we're going to want to turn that into a weight. So I'm going to go ahead and do that right now. So remember, weight equals mass times gravity. So we've got 57 megagrams, which is 57,000 kilograms. Okay, times the gravity, which is 9.81 meters per second squared. Okay, so that weight equals, let's see, 550 9,170 kilonewtons or newtons, but I just converted it into kilonewtons because, Anyway, so a cylindrical object with a mass of m is partially submerged in water. So the partially submerged is annoying and connected to a pulley that attaches to a 10-meter wide gate. If H, capital H, is 6 meters, and lowercase is 4 meters, determine the buoyant force acting on the cylinder. Okay. All right. Okay, so we want the buoyant force acting on the cylinder, the force of pressure of the water on the gate, and if the gate will open. Okay, so this one, everybody would have gotten a different answer as to whether or not the gate would have opened based on this weight right here, I assume. Or maybe I did it so that everybody's was going to be, closed, or everybody was going to be opened or something. I don't know exactly. But anyway, I imagine I made it so some people's would open and some people's would close. Anyway, so the buoyant force acting on the cylinder. Okay, so buoyant force, equals gamma of the fluid times the volume displaced. Okay, so the volume displaced, what I'm looking for here, I'm going to erase this 57 megagrams. So the volume displaced is the volume that is essentially underwater. So, so that's this volume right here. Okay, and sorry, I meant to draw those lines all the way down. So that has a height of 3 meters and a diameter of 1 meter. Okay, so the force of buoyancy equals the gamma of the fluid. So this is water, so I'm going to say the gamma of the water times the volume displaced, which is going to be the volume of the cylinder. So pi r squared, that's the area of the bottom, times the depth of this thing. Okay, so that depth, of course, is 3 meters, and it's 3 meters is the height of this cylinder. Okay, so the FB equals gamma water, which let's see, we're in meters. So that's 98. Hey, you're okay. You're okay. 9810 newtons per meter cubed times pi. The radius of this thing, well, it's a 1 meter diameter, so that's 0.5 meters squared times the height, which is 3 meters. FB equals, so I guess this is part A. Let's see, so we're getting 23,114 newtons. Okay, so this buoyant force is rather insignificant compared to this. Okay, this is a very dense material. But anyway. All right, so then B, what's the force of pressure of the water on the gate? Okay, so B. So we're looking for something totally different now. Let's see. Well, I'm going to go ahead and box this, so it reminds me not to erase it as I work through this problem. Okay, so for part B, this gate is, so the water is right here. Okay, and it's like, this is the pressure prism. Okay, and I need to know what is the force of pressure on that gate. Okay, so, how do we get that? Well, we do that the way we've always done it. The force of pressure equals gamma of the fluid, in this case that's water, times the height of the centroid times the area. Right, now this one's kind of nice because it's a rectangle, right? So, this shape right here is rectangular. So what does the rectangle look like? Rectangle. Okay, well, it looks like this. Okay, it's 4 meters high, and it's how wide? 10 meters wide, 10 meters wide, 10 meters into the page. Okay, so I'm going to go ahead and get all the things for it because, the centroid is right here. So the HC and the YC are both the same, because remember the HC is going from the water surface down to the centroid, and the YC, vertically, and the YC is following the surface of the gate down that same distance. Okay, and in this case, since the gate is vertical, it's the same for both. So there's going to be 2 meters and 2 meters. And then the area of this gate is 4 times 10. So that's going to be 40 meters squared. And then the IXC usually for a rectangle is 1/12 the base, which is 10 meters, times the height, which is 4 meters cubed. Okay, so that's some number. Okay, like 53.333 meters to the fourth. And as I've told you guys a million times before, I hate those units because it doesn't really mean a whole heck of a lot to me. Okay, so anyway, so let's go over here to the FP in here. And once we've done this, it's really just plug and chug for, finding the force of pressure. So I can say, okay, the force of pressure equals the gamma of the fluid. Well, that's 9810 newtons per meter cubed. The HC is 2 meters, and the area is 40 meters squared. So the force of pressure is, 784,800 newtons. Okay, now you can see that number is at least, maybe it can compete. So they're of the same order of magnitude, more or less, right? Okay, so then this last bit here is, let's see here. I think we want to know, let's see. let's erase some of this. Okay, because we're really going to want to get in, we're going to want to kind of dig into this gate here. Come on, you can do it. Oh, man. Okay, so this little h is 4 meters, and this one is 6 meters. Okay, so the first thing that I kind of want to get at is the tension, what's going on in this line. And let's see here. So basically I want to know, like, how hard is this thing pulling, right? What is this force right here? Okay, and really the way, if we really wanted to analyze it, we would look at like this weight, because basically the weight has, the weight has a weight going down of 559.170 newtons, and then it's got, presumably anyway, it's got a tension going this way, and it's got a buoyant force of this number right here, 23,114 newtons. So if this thing is not moving, which is the assumption we're going to make, because the last thing is if the gate will open. So we're going to assume that it's not going to open. And I'm going to go over here and I'm going to say, based on this is my free body diagram of that weight. I've got a tension and I've got a buoyant force going up, and I've got the weight of the thing going down. So tension has to be greater than or equal to the difference of those two in order for this thing to not move. Well, really, it's got to be equal to, right, for it not to move. Equals for no motion. All right, so let's see here. So let's do that subtraction real quick. 559,170 minus 23,114. Okay, and we're going to get 536,056 newtons. Right? It sucks working with these big numbers. Excuse my my French. Right? So 536,056 newtons. Okay. So what that means is that I can go down here to C, and I could say, okay, for that to be the case, let me draw the free body diagram of the gate. Okay, and it looks like this, more or less, right? Quick and dirty, right? So here's a hinge. So at the hinge, I've got HX, I've got HY, okay, and I've got a tension up here, which we know how big it needs to be. And then I've got the force of the pressure, right? So to solve this thing, the easy way or whatever, or the what we're thinking at this point is we're going to say, okay, well, the sum of the moments around H equals 0. Okay, so I've got FP times this moment arm, which I don't know what that is yet. What do we call that? We'll call that Y maybe, times Y. Okay, and so that's causing it to spin this way, so that's a positive, right? Minus the tension times its moment arm, which is this whole distance here. And we know that, actually, that's 6 meters, that's given, equals 0, right? So that's this capital H. So maybe I'll leave it as capital H for cleanliness, because it'll match, with the fact that I don't have any of these other variables plugged in yet. So let's see. Come on, baby. You can do it. Okay, here's a capital H. All right, so this little y is what we need right here. We need the distance, to that FP, right? So FP is like right here. And the way we get it is we need this distance right here, which is called YCP. Okay? How do we get YCP? How do we get YCP? Right? This little distance right here, this is 4 meters minus YCP. Okay? And so that's really what we're looking for, is 4 minus YCP. But to get YCP, we use our equation YC plus IXC or XX or whatever over YCA. Okay, so YCP equals, let's see, YC is 2 meters plus IXC, which is this number, 53.333 meters to the fourth, divided by YC, which is 2 meters, divided by the area, which is 40 meters. Right, so YCP equals, 2 2/3 essentially. Okay, which means this distance we're looking for right here, which I've called Y, Y is going to be 4 minus that, which is 1.3333 meters. Okay, so we'll go back over here, and so this is 1.3333 meters. This is 6 meters. Okay, and so we'll go ahead and plug in. So FP is 784,800 newtons times Y. What was Y? Oh, 1.3333 meters minus the tension in the rope. Oh, let's go ahead and solve for the tension in the rope times H, which is 6 meters, equals 0, right? I have a tension up here, but that's really a critical tension, right? If the tension is greater than this number, then that means this fluid is going to go that way. I mean, the weight is going to rise. And if the tension is less than that number, then the thing will fall, right? Yeah, anyway. Let's go ahead and get a tension first, and then we'll think about this. So tension equals. Okay, so this is the tension. This is the tension required to overcome the weight of the water, or the pressure of the water, to overcome FP. Right, so 174 kilonewtons. Okay, it turns out we've got this many kilonewtons, okay, which means gate will open. Okay, all in all, this is one of the hardest problems I've ever put on a final. I mean, hard is a little bit strong, only because this part was straightforward, this part is straightforward, but this last little bit, just thinking about, well, what is this tension? Okay, and what is the actual tension on the rope? So this is the actual tension on the rope at the moment that this thing is this deep in, right? Because as soon as it starts to move, if it moves in that direction, or if it moves in any direction, the buoyant force will change. But the buoyant force isn't terribly important here, right? Because it's relatively small. So anyway, so yeah, so this C part was a bit of a doozy. It kind of took some slowing down and thinking about it. So just be aware of that. All right. Consider the pipe shown below. I love it when they tell you to consider a pipe shown below. Okay, so we've got a fluid with some density flowing in location 1. It's split into 2 smaller pipes with discharge to the atmosphere. Okay, determine the horizontal force required to hold the pipe in place. Okay, so when we approach something like this, let's see, the horizontal force. So, so we're doing a force on a moving fluid, which means we're going to be doing the momentum equation. And it only wants horizontal, so we're going to go in the x direction. So sum of F in the x plus the summation in of rho Vxq equals summation of the outs rho Vxq. Okay, notice for the ins, I've got 1 location, and for the outs, I've got 2 locations, right? So let's consider a little free body diagram over here of the pipe. and water. Okay, why do I want the pipe? Because this is a question about holding the pipe in place. Okay, so here's my pipe. This one's closed. Those two are open to the atmosphere. Okay, so I'm going to go in here and just draw on this, right? So I've got this one's a pipe, so it's got a little pressure right there. So I'll call that P1A1. Okay, it's an enclosed pipe, so it's pressurized, right? Otherwise, let's see here. I've got the weight of the water. I've got the weight of the pipe. Okay, luckily I don't have to worry about those, right? Those are going down, and this is a question in the X direction. And then I've got a force to anchor it. Force to anchor in the Y or Z direction, which, again, we're not going to worry about that. Force to anchor in the X direction, right? Beautiful. All right, so then the only other things we need to deal with is we've got fluxes. So V1, V2, and V3. And remember, there's no pressure at 2 or 3 because it's going out into the atmosphere. Okay, so these are the things that we need to deal with. Okay, so I'm going to expand this equation down here based on that free body diagram, and that will kind of tell me like what it is that we need to solve for. Okay, so the forces in the X direction. I've got FAX, that's what we're looking for. I've got plus P1A1. Okay, that's in the X direction. Those are all my forces. Okay, I've got an in right here of V1. So I'm going to go plus rho V1, okay, Q1, I guess, equals. Now we've got two outs here. So I'm going to need to do, so the first one is going to be, now remember we're only dealing with the X direction, so it's going to be rho. We'll call this V2, but we're only dealing with the X direction, so that's going to be the sine of 60 degrees based on this right here, using this angle right here, because that's the opposite side, times Q2. Okay, and then I'm going to do, and that's in a positive X direction, so then I'm going to do rho V3, and that one's just in the straight direction, so we don't need an angle on there. We'll call that Q3. Okay. So that's pretty much the whole thing. Now we just need to see what it is that we don't know, right? So once we're here, let's see what we know and what we need, okay? So we've got P1 from right here. The area, of course, we can, it actually gave us the area, so we don't even need to do pi d squared over 4 because it just gave us the area. Let's see here, V1. We don't know what V1 is, so V1 is this is a big question mark. Okay, did it give us Q1? I don't think it gave us Q1 either, so that's a question mark. That's problematic. All right, what about V2? Well, they gave us V2 is this, and they gave us, well, we don't need A2 yet, not directly anyway, so we know V2. And we can get Q2 from multiplying these two, right? And we have V3 given, and we can get Q3 by multiplying these two, right? Okay, so let's go ahead and get some of those values here, just because I think it's going to be helpful to do that. So if I multiply these two, V times A, I get Q2, and if I do V times A here, I'm going to get Q3. Okay, these numbers are like nice and clean. So Q2 is 0.2 meters cubed per second, and Q3 looks like it's 0.4 cubic meters per second. Okay, so those are fairly clean. You didn't have to do it right here. You could have just plugged them down into these equations. It's kind of up to you. All right. So then, what does that mean? Q1 is well. Q1. Okay, it's going to be whatever comes in is going to have to leave what's leaving, right? So if this is leaving and this is leaving, then Q1 is 0.60 meters cubed per second, right? Because it has to be the same as what's leaving. And then if I divide that by this area right here, I can get that V1 equals 0.60 divided by 0.1, so it's going to be 6 meters per second. It's really cooking on this end. Okay? And I think that gives us everything we might need for this problem. Okay? Let's just start plugging in and we'll find out. Okay, so FAX plus P1, 200 kPa, 200,000 newtons per meter squared. Be careful because pressures are almost always given in kPa, so just convert that into regular PA. It's going to make your life a lot easier. Times that area, which is this guy right here, so 0.10 meters squared, excuse me. Plus the rho. What was the rho here? Oh, what an annoying rho, right? 326 kilograms per cubic meter times V1, which is 6 meters per second, times Q1, which is 0.6 meters cubed per second, equals rho, 326 kilograms per meter cubed, times V2, that's this number right here, times 20 meters per second, times the sine of 60 degrees. What's the sine of 60 degrees? Is that root 3 over 2? Yes, it should be. Okay, and then we've got a Q2, which is 0.2 cubic meters per second. Okay, so that's this term, and now we need to get this one, plus 326 kilograms per cubic meter times V3, which is this number right here, 20 meters per second, times Q3, which is 0.4 cubic meters per second. Boy, when I made this exam, I didn't give a lot of space for this problem. All right, so I'm going to pause it while I plug and chug this in my calculator. Actually, I can do some of these in my head, right? So this one's 20,000 newtons, right? Newtons plus. Okay, so it comes out kind of like this. And I think what you'll see here is that this pressure term is really just going to kind of overpower everything else. So we're going to end up with a negative number. So basically, the principal thing that's happening is that the anchoring force is going to be pushing back against this P1A1, right? And there's a smaller effect from these momentum fluxes, but they don't really matter in this case, or at least not too much. So 17,436.3 newtons. Okay, so FAX equals 17.4 kilonewtons going that way, right? Okay, so that's how we do that one. All right, so let's see here. Ooh, a rectangular tank. Nice. Okay. All right, so a rectangular tank with the bottom area of 612. So we've got a tank. Okay. Its bottom area is 612 inches squared. It's filled to a height of 73 inches, so it's got some fluid in it. I don't particularly like my drawing, but 73 inches with a mass, so the liquid is 73 slugs. Okay, determine the fluid's weight, density, and specific gravity. Okay, let's see here. Weight equals, okay, so A. Weight equals mass times gravity, or weight equals gamma times the volume. Well, let's see here. I don't know the gamma, so we can't use this one, so let's use this one. Okay, so weight equals 27 slugs, okay, times gravity, which is 32.2 feet per second squared. So the weight equals whatever that is. Let's see here, 869.4, and this is going to have units of pounds, right, because a slug foot per second squared is a pound. To give this 3 sig figs, you would say 869 pounds. Okay, cool. Let's see here, density. Okay, B. Density, okay, so rho equals mass divided by volume. So that's probably the easiest way to get at this. So let's go ahead and do that. So rho equals the mass, which is 27 slugs, divided by the volume, which is the bottom of the area, 612 inches squared, times the height, which is 73 inches. Okay, so rho equals, this is going to be an annoying number, right? 27 divided by 612 times 73. So it's really small. So 0.0006, 0.4351. Okay, now this is in units of slugs per inches cubed, and there's no reason why I would not accept that answer. It's a completely miserable answer, but it's certainly acceptable because it's true. Ideally, you would want to multiply this by 12 cubed in order to get slugs per cubic foot. Okay, so in slugs per cubic foot, this is 1.0443 slugs per cubic foot. Okay, so that conversion just makes this a lot nicer to work with. Okay, for the answer that you would turn in, of course, you would what? 1.04 slugs per cubic foot. Okay, so the last thing is we want specific gravity. So we want to compare that to the specific gravity of water. I mean to the specific weight of water, the density of water, sorry. So C, okay. So S of this fluid equals the rho of the fluid divided by the rho of water, right? So this fluid is 1.0443 slugs per cubic foot. And the density of water is, now remember, if you forgot the density of water, remember you take 62.4 and you divide it by 32.2, okay, and you get 1.94. So 1.94 slugs per cubic foot, right? And so if you divide those, we'll get what, 0.53889, or really this specific weight, specific gravity of the fluid is 0.539. Okay, so that's how we do that one. Okay, so let's go down here. Oh no, we have a Moody problem, which means, well, when we get there, I'm going to have to import a Moody diagram. But for now, let's work this sucker. Determine the power required to pump water at a flow rate of 51 cubic meters per second. Okay, we got Q. From the lower reservoir to the upper. The loss coefficient K for smooth pipe entrances is 0.5. For smooth pipe bends is 0.3. And for pipe exits is 1.0. The pipe is made of clean cast iron and has a roughness, epsilon, usually, 0.3 millimeters. So let's put that in terms of, well, you know what, the pipe is in millimeters here, so we can use 0.3 millimeters, right? Because that ratio is going to be what matters, so we'll kind of leave it like that. Okay, you may assume alpha equals 1.0. So for my students who hate calculating Reynolds numbers, there you go, that's your way out of doing that. Okay, so let's see here. So what are we looking for? We're looking for the power required to pump water. So to get power equals gamma HPQ, right? Then we know Q is given. We know gamma because it's water. So what we want to know is HP equals what? So the only way to get at HP is to do a nice little energy equation, right? So we've got P1 on gamma plus Z1 plus alpha V1 squared on 2G plus head of the pump equals P2 on gamma plus Z2 plus alpha V2 squared on 2G plus HT, I don't see a turbine in this problem, plus the head loss. And I'm going to go ahead and expand the head loss into, let's see here, the head loss due to friction and the head loss due to the minor losses, right? Okay, and usually since there's a bunch of these, we're going to put a little summation right there. Okay, so let's see what we've got here. All right, so let's pick some locations. Usually in these cases, the easiest thing to do is to make this point 1 and to make this point 2, because we know in those locations that the pressures are atmospheric, in both of those locations. Z1 and Z2, well, those are basically given as 200 and 235. So basically I'm going to make Z2 35 meters and Z1 my datum, because why not? Okay, V1 and V2. These, it's interesting. You may assume alpha equals 1.0, but you didn't need to, because it just goes away because of the Tahoe assumption. Okay, let's see what's left. HP is left on the right, on the left-hand side, and that's what we're looking for ultimately. There is no turbine, and we have to deal with these loss terms. Okay, so let's see. So if we rewrite this, we get HP equals 35 meters. So basically the pump is going to have to raise this fluid by 35 meters while overcoming HF, which we generally at this point will write as FL on D V squared on 2G. So that V squared refers to the velocity in this one pipe. We only have one pipe, so that's nice. And then plus the sum of K, the sum of HL, right? So that's going to be the sum of K times V squared on 2G. And again, there's only one velocity in this whole thing, so I don't really need to label that V, right? It's pretty straightforward. Okay, so let's see here. So the sum of K's, let's not get ahead of ourselves. So HP equals 35 meters plus F is unknown at this point. Let me write F in blue because we're going to have to go looking for that, right? L on D. Well, what's the length of this pipe? Does it say the length of the pipe? I guess it's 100 meters going this way, and then it looks like it's going to be 40 meters going this way, right? So it's 140 meters. 140 meters. Okay, what's the diameter of the pipe? Well, through the whole thing, the diameter is 300 millimeters. So that's 0.3 meters. Okay, and then I've got a V squared on 2G. I'm going to go ahead and pull that V squared on 2G kind of out to the front because I don't want to deal with it just yet. Right, and then I need to add the sum of K's, and this V squared on 2G has been pulled out. Okay, so the sum of K's, I've got 0.5 plus 0.3 plus 1. Okay, those are all my little losses, right? So it's going to be plus 1.8. Right? Now this V squared on 2G, and this problem is kind of interesting because, or it's just unusual in some ways, because it's pretty easy to get, right? We've got Q, and we know the diameter of the pipe. So I know what my V is pretty much everywhere. If I just do a little aside, and I need to do my continuity. So I've got Q equals VA. So what do we say? 51 cubic meters per second. 51 cubic meters per second equals V times A, which is going to be pi times 0.3 meters squared over 4. Okay, so V equals, so this is 729.50 meters per second. That's such a huge number. But I guess such is life. Okay, so from this, a lot of times I'll just go ahead and say, well, what is V squared on 2G? Because I've already got it in my calculator, right? So I can just kind of take that number and square it, and then divide it by 2G, in this case is 19.62. And I'll end up with, like, in this case, a really massive number, 26,532 meters. Okay, and I guess that's what happens when you get a velocity of something this huge. And of course, what's the problem? Again, these flow rates are massive through fairly narrow pipes. Okay, so I've got 51 cubic feet per second going through a pipe that's 30 centimeters in diameter. Okay, so for those of you who are not familiar, 30 centimeters is less than a foot. Okay, 51 cubic feet. Cubic meters. Cubic meter is roughly 35 cubic feet. So you can kind of imagine. We've got like 900 cubic feet going through a pipe. Every second going through a pipe that's about a foot in diameter. So it's going to create some very large velocities and some very large velocity heads. Okay, so anyway, so now we've got all of that. So now we're looking at this and we're like, okay, so I can plug that in for V squared on 2G. I can go ahead and do that right now, right? I can go, okay, let's erase this sucker. And let's just write down this, rather ridiculously large number, 26,532 meters. Okay. So then the last thing I need to do is I need to get this F right here. Now remember, F is a function of the Reynolds number and the relative roughness. So we need to get both those things if we can, ideally, right? So let's see here. So epsilon on D equals, well, the roughness was 0.3 millimeters. 0.3 millimeters, and the diameter was 300 millimeters. So epsilon on D is 0.001. And I'm such a clown, I have to sorry, this is millimeters. I have to plug those in, or I'm gonna like screw up the the moving of the decimals. Anyway, so there you go. And then the Reynolds number. Okay, let's see. That's VD on nu. Okay, so the velocity is this massive number, 729.50 meters per second. Okay, the diameter was 0.3 meters. And the viscosity, this is the whatchamacallit system. So the viscosity is, give or take, 10 to the minus 6 square meters, okay? Square meters per second. Okay, so if we plug that into our calculator, we'll get the Reynolds number is, okay, hold on. Brief typo, this should be 721 and not 729. It's not going to really make a difference. But still, if you're following along with your calculator, it will show up and you'll go, what's going on here? This number is correct, since that was all inside my calculator. Is that right? I think it's correct. Yeah, that number's correct. It should be correct. Yeah. Okay, right. Okay, so this should be 721. Okay, we get a Reynolds number here that is, quite simply off the chart. 2.1 times 10 to the, let's see here, 1, 2, 3, 4, 5, 6, 7, 8. 10 to the 8th. So that's like really massive. Okay, but these are the two numbers that we're going to need for the Moody diagram. So let's give it a second, and I'm gonna pull up a Moody diagram. Okay, and the cool thing here, and we didn't really mention types on this particular problem. This might be the first exam I ever gave that didn't have a type 2 or a type 3. But anyway, so we've got the Reynolds number, and we've got the relative roughness, which means we're not going to have to iterate. We're just going to go get our number. Okay, so we need 0.0001, which is right here. I think. Let's see. Let's zoom in. Oh, that's too many zeros. It's right here. Okay, and then we've got 2.1 times 10 to the 8th. So we zoom in, 2.1 times 10 to the 8th. So we're off of this diagram. Here's 10 to the 8th. We're like right out here somewhere. Okay, if I judge by this scale here, it's going to be, I guess this will be a little bit further out this way. But, we're in the flat region, right? So that should be okay. Okay, so this is our, so this right here is our line. Okay, this line right here. Okay, and we're just going to follow it flat, right? Because we're technically out here somewhere, and we're in the region where the Reynolds number doesn't really matter, right? It doesn't matter if we go higher or lower. I'm going to draw this as best I can, and you could probably see that I'm messing it up a little bit, but I'm doing the best that I can. And it's going to come in about like that. Okay, so, we're at like 0.0, I don't know if this is 1/8, this is 1.9195, somewhere in there. Okay, obviously, or maybe it's not obvious to you, but, I have to give you a little play on that, right? So 0.0195, so that's going to be our F. Okay, so let's go over here. And we will plug that in where I see this F, right? So I'm going to go ahead and erase that F. And I don't know why everything got blurry. But anyway, so this is going to be 0.0195. Okay, that looks really, really ridiculous. But, whatever. So let's go ahead and let's solve this. And so I'll get HP equals. Okay, we get this absurdly high number. Okay. And notice that, raising at this elevation wasn't really a big deal. However, overcoming all the friction was a huge deal. Why? Because it was going so screamingly fast through the pump. Again, this is, essentially my error, or not my error. Well, it is my error, but it's what happens when you try to make an exam and everybody gets different numbers. So this is a bit of an unusual number, okay? But anyway, the ultimate question for this problem was, what is the power required to pump the water? So the power then is going to be W dot equals gamma HPQ. So W dot equals gamma, which is 9810 newtons per meter cubed, times HP, which is 289,230 meters, times Q, which was what, 51? Yeah, 51 meters cubed per second. Okay, so these meter cubed are going to cancel. I'm going to be left with a Newton meter. That's a joule. A joule per second is a watt. Okay, so we're going to take this number in my calculator. I'm going to multiply it by 51, multiply that number by 9810, and I'm left with some absurdly massive number, which is 1.4471 times 10 to the 11th, okay, watts. Okay, usually we don't really like watts all that much. I would be inclined to make this to the 10th and then to the 9th. So we'd end up with W dot equals 145 times 10 to the 9th watts, or better yet, W dot equals 145, and these would be gigawatts. I never get to use gigawatts. Oh, the best I ever get is megawatts. But anyway, so there you go. Okay, last thing here. Before you turn this in, make sure you have the correct numbers, correct units in all your answers, 3 significant digits, and you've answered all 3 parts of numbers 4 and 6. 3 sig figs here. Good. Units. 3 sig figs, should be no units there. I don't know if this is showing up blurry on your screen, but it's showing up blurry on my screen. But I definitely answered A and B. Well, it's coming out blurry, so I'm just going to hope that I did that. I guess on this one the answer is gate will open, so there wasn't really a numerical answer. But for part B here, this FP should have been 785 kilonewtons if we want 3 sig figs. The FB should be 23.1 kilonewtons if I want 3 sig figs. And I guess I could convert this one, but it wasn't specifically asked for that number. Anyway, everything's coming out a little blurry at this point. This one has 3 sig figs and an answer. So maybe this video is going a little long. Anyway, so that's it. That's all I got, and that's the exam. So hopefully this is helpful for you guys. Anyway, good luck studying, and hopefully you don't need it. As they say, luck is for the ill-prepared, or something along those lines. Anyway, and take care of yourselves as always. All right, take it easy.